Hi everybody, we're going to begin our discussion of basic hydraulics, which as you read in the module is the study of fluids in motion, and that certainly describes irrigation systems. And therefore, basic hydraulics are going to be really important as we begin learning about designing irrigation systems. But to begin with, let's start with some basic water facts. For example, we know that 1 gallon of water weighs 8.33 pounds. We also know that 1 cubic foot of water weighs 62.4 pounds. And I'm introducing these facts about the weight of water, in particular pounds, because of how that relates to pressure and how it relates to the pressure that you might measure in an irrigation system. So we think about water in terms of how much it weighs. There are also 7.48 gallons of water in 1 cubic foot. And an acre foot of water is the amount of water that would cover 1 acre of land to a depth of 1 foot. And it's the equivalent of about 325,850 gallons of water. So that's a pretty significant amount of water. And that unit, acre feet, is often used by states or by cities to describe the amount of water they use or deliver to their customers or residents. Now, another unit of water that's commonly used, especially for billing, is hundreds of cubic feet, or CCF. You might see it noted as CCF. And a CCF, or 100 cubic feet of water, is about 748 gallons. If you can imagine this cube being full of water, and also make note that it's 12 inches long, 12 inches high, and 12 inches wide. You can imagine that there is 1 cubic foot of water resting at the base of this cube. Now from the previous slide, we know that 1 cubic foot of water weighs 62.4 pounds. So that's the weight of the water that would be measured if this cube were sitting on a scale. Now the area at the base of the cube is 12 by 12 inches, or 144 square inches. If you were to divide the 62.4 pounds resting at the base by 144, it would equal 0.433 pounds. So at the base of this particular column, this shaded column of square inches here, there are 0.433 pounds resting at the base. So that would also be equal to 0.433 pounds per square inch. And this is where we start getting into the terms relating to pressure, pounds per square inch. And 0.433 pounds per square inch is a constant that we'll be using a lot in the course. We'll go over it many, many times. So another thing to note here is that the height of the water here is 12 inches or 1 foot, right, for this shaded column. And we know already that it's creating a pressure of 0.433 psi at the base. And that introduces this second way to express pressure, which is known as feet of head. And so at the base of this column, there is 1 foot of head just at the base of this column. Now let's look at a couple of other examples of that. Now in this image of a water tank, you see from point A here to point B is 100 feet. It's a distance measured of 100 feet. So again, we're talking about that measure, feet of head, for water. So let's now consider these two pipes. This one is 6 inches in diameter and this one is 2 inches in diameter. But really the pipe size here is not very important. If we were to try to figure out what the feet of head measurement would be at the base of these pipes, this is the measurement that is important. It's 100 feet to the top of the water in this tank to the bottom of the water in these pipes. So in both cases, there are 100 feet head of water at the bottoms of the pipes. Again, the pipe size isn't important. The total depth of the water is what's important. Now moving on. In the figure at the left, you can see that a column of water, kind of like that first cube I showed you, 1 foot high and 1 foot square, creates a pressure of 0.433 at the base. So if you were to add an additional foot of water on top of this, the pressure would double to 0.866 psi, so just 0.433 times 2. In the figure on the right, another constant is illustrated. If you had a pressure gauge at the base of this column and it were reading 1 psi, the height of water to give you that pressure at the base is 2.31 feet. That's another constant that we're going to use quite a bit in the class. So these are the really important facts I want you to remember at this point. 1 psi is equal to 2.31 feet of head. We just went over that. And also that 1 foot of head is equal to 0.433 psi. Now let's consider what the pressure would be at the base of these three containers, okay, A, B, and C. The question is, does the shape or size of the container make a difference in the pressure at the bottom? Let's think about that for a minute. The weight of the water in all of the columns at an equal depth creates the same pressure resting on 1 square inch. So if you're only considering 1 square inch, it doesn't matter what the size or the shape of the container is. Now this might seem a little strange or not possible, but remember, pressure is measured as the force on 1 square inch, not the total weight. So imagine that you pressed your thumb and your thumb had an area of 1 square inch to close a hole in the bottom of this tank. Your thumb would only feel the pressure from the height of the water directly above it. It wouldn't feel the pressure from the entire amount of water in the tank. Now let's think about it in another way. What if you dove into a swimming pool or a lake? You know that the deeper you go, the more pressure is going to build in your ears, right? And that pressure doesn't change if the pool has a different shape. And it doesn't change if you're diving into a lake as opposed to a pool. The pressure at any depth is dependent on the height of the water column above you at that point. So what this means in terms of irrigation systems is that when sprinklers or drip emitters are at different heights, or when irrigation pipes follow the contour of the land, there will be a difference of 0.433 psi for every foot of elevation change, and that will be positive or negative depending on whether the change is upward or downward. So we'll continue with another lecture on basic hydraulics, but first here's some more food for thought.